For many years, researchers thought they had a reasonable handle on the scale of everything. The universe was unimaginably large, yes, but still something you could put numbers on. Roughly 14 billion light-years stretching out in every direction, filled with a few 100 billion galaxies spread across the cosmic landscape. It sounded overwhelming, yet somehow contained, as if the whole thing fit neatly inside our equations. That sense of certainty lasted until the James Webb Space Telescope began to stare into regions that looked like pure darkness. And with that simple act, the old picture started to fall apart. What Webb showed us was an observable universe, far larger than expected. Almost 93 billion light-years from one edge to the other. Instead of emptiness, it uncovered dense fields of stars in places where we assumed there was nothing at all. It revealed mature, well-organized galaxies already in place just 300 million years after the Big Bang, appearing far earlier than our models ever suggested they should. It spotted black holes gaining mass at a pace that challenges what we thought physics would allow, and enormous structures that seem far too big to exist at such an early stage of cosmic history. Yet the most disturbing part of these findings isn't simply how deep Webb can see. It's what all of this quietly hints at. These observations force us to think about what lies beyond the boundary of what we can observe, beyond our cosmic horizon. They suggest that the universe may be vastly larger than even these staggering numbers imply, and that most of it could remain permanently out of reach, no matter how advanced our technology becomes. If you're ready, hit that like button, subscribe, and let's discover together what James Webb found, this time to really grasp what the James Webb Space Telescope is showing us. We have to let go of the everyday idea that space is simply something we look across, like a vast, empty stage. In the universe, distance cannot be separated from time. Light always travels at a fixed speed, about 186,000 miles per second. Nothing moves faster than that. At that pace, light could circle Earth more than 7 times in just 1 second. And yet, even this incredible speed is not enough to eliminate delay. The moment light begins a long journey, distance becomes a measure of how far into the past we are looking. The longer the journey, the older the image by the time it reaches us. When you look at an object a mile away, you are seeing it as it was a few millionths of a second earlier. When you look up at the moon, you are seeing light that left its surface 8 seconds ago. When you look at the sun, you are not seeing it as it exists right now, but as it was 8 minutes in the past. The sky above us is not a live broadcast of reality. It is a flow of delayed information, arriving continuously. These delays are so tiny at human scales that we never notice them. Our minds naturally assume the world is immediate and uninterrupted. But as we look farther and farther outward, those delays grow larger, and eventually they change how we must think about the universe itself. The closest star beyond our sun appears to us as it was more than 4 years ago. The core of the Milky Way is visible to us only as it existed 26,000 years in the past. And once we look beyond our own galaxy, into the immense spaces between galaxies, we are no longer observing the universe as it is today at all. We are seeing earlier stages, earlier chapters of a story that has already been unfolding for billions of years. The night sky, therefore, is not a frozen image. It is a vast archive. Every point of light arrives with a built-in timestamp. Every photon carries a message from a specific moment in cosmic history. The farther away the source, the older the message it delivers. The complication is that these messages do not arrive unchanged. As the universe expands, space itself stretches. And when space stretches, it stretches the light moving through it. The wavelengths of that light grow longer. Energetic blue and ultraviolet light gradually shifts toward red, and then continues into the infrared. This phenomenon, known as redshift, is far more than a simple change in color. It is a physical record of how much the universe has expanded since the light first set out on its journey. Redshift works like a cosmic clock. The more stretched the light becomes, the longer it has been traveling, and the earlier in the universe's history it must have been emitted. For many decades, astronomers depended on telescopes designed mainly to observe visible and ultraviolet light, the small portion of the spectrum that human eyes evolved to detect. Observatories like Hubble revolutionized our understanding of nearby galaxies, regions where stars are born, and the large-scale arrangement of matter across the cosmos. But when scientists tried to push their view deeper into the past, the universe seemed to grow dim, not because it stopped existing, but because its light had transformed. The oldest galaxies did not vanish. Their light simply shifted beyond the range those instruments could see. The James Webb Space Telescope was created to chase that lost light. Its primary mirror measures more than 21 feet across and is covered with an extremely thin layer of gold, selected because gold reflects infrared light with remarkable efficiency. Webb does not circle Earth like many other telescopes. Instead, it operates nearly 1 million miles away at a carefully balanced gravitational location where it can remain stable and keep its gaze fixed with extraordinary precision. Protected from heat and blinding sunlight by its distant orbit, Webb can remain incredibly cold, and that cold is absolutely vital. Infrared light is deeply connected to heat, and if the telescope itself were warm, it would overwhelm the faint signals it is meant to sense. Webb had to fall into near silence, quiet enough to listen as the universe murmurs. When Webb turns its gaze toward a patch of sky that looks completely dark to human eyes, it isn't hunting for nothingness. It is waiting, patiently, for photons that have been stretched almost beyond recognition by billions of years of cosmic expansion. Those photons drift in slowly, sometimes arriving one at a time. Webb may focus on the same tiny region of sky for hours, even days, carefully gathering light that has traveled across nearly the entire observable universe. And what emerges from that darkness is not a calm, hesitant cosmos just starting out. What appears instead is a universe already alive with activity. Some of the galaxies Webb has uncovered formed when the universe was only about 300 million years old, less than 3% of its current age. To understand just how early that is, imagine squeezing the entire history of the universe into a single calendar year. In that scale, these galaxies would show up on January 2nd. According to long-standing theories, this period, often referred to as cosmic dawn, should have been faint and subdued. The first stars were expected to ignite slowly. Early galaxies were thought to be small, delicate gatherings of gas and stars, needing hundreds of millions of years to grow into anything substantial. But Webb found galaxies that were already shining brightly, already massive, and already forming stars at remarkable speeds. Some were so luminous that even if they were far more distant, Webb would still be able to detect them. That brightness is crucial. Bright galaxies require vast numbers of stars, and stars do far more than glow. Deep inside their cores, they manufacture heavier elements such as carbon and oxygen, elements that simply did not exist in the universe's earliest moments. These elements are released only when stars reach the end of their lives. So when Webb detects heavy elements in such young galaxies, it is uncovering clear evidence that earlier generations of stars must have already formed, lived, and died. The universe had already passed through several cycles of creation and destruction much earlier than expected. The cosmic clock was being forced backward. Complexity did not creep in slowly, it surged forward. There is also something quietly profound about the act of observing this ancient light. Webb does not capture these images in an instant. It collects photons that have been traveling for more than 13 billion years, photons that began their journey when the universe was young and unfamiliar. When that light first set off, Earth did not exist. The sun had not yet formed. The Milky Way was still assembling from clouds of gas and dark matter. Oceans, life, civilizations, and every chapter of human history unfolded while those photons were already on their way. By the time Webb finally detects them, we are not watching events as they happen. We are seeing moments that occurred once, long ago, preserved in motion, and never repeated in quite the same way. This is why astronomers say the James Webb Space Telescope does not just look far away, it looks backward through time. Distance becomes a timeline. Nearby objects reveal the universe closer to the present, while distant ones expose earlier and earlier stages of cosmic history. Yet even Webb's extraordinary vision runs into a hard limit. No telescope, regardless of its power, can see beyond a boundary imposed by physics itself. That boundary is set by how far light has been able to travel since the universe began. It is known as the observable universe, a vast sphere centered on us with a radius of about 46.5 billion light-years. Webb is now pushing observations closer to that edge than ever before, detecting galaxies at distances once thought impossible to reach. But even Webb cannot see beyond the cosmic horizon. And this is where the realization becomes unsettling. Space does not simply end at the limits of our vision. Beyond that horizon, galaxies continue to exist. Stars still ignite and die. Black holes still collide. Entire cosmic histories unfold in regions that will remain hidden from us forever. Not because our tools are inadequate, but because space itself is expanding too rapidly. Webb has not only revealed how far we can see, it has revealed how much of the universe lies permanently beyond our reach. As we absorb what Webb has uncovered within our observable bubble, the early brilliance, the rapid rise of structure, the sheer number of galaxies, a deeper question begins to surface. If so much exists within the small fraction of the universe we are able to observe, what does that imply about the true scale of everything that lies beyond our view? For much of modern astronomy, the early universe was pictured as a quiet and fragile place. After the Big Bang, space expanded swiftly, temperatures fell, and matter spread out almost uniformly in every direction. There were always tiny irregularities, small ripples in density where matter was just a little thicker than its surroundings. Gravity, in our understanding, would slowly take advantage of those differences, gently drawing material together over immense stretches of time. In that view of the early universe, the first stars switched on hesitantly. Gas clouds needed long periods to cool down. Dark matter halos had to grow gradually before they could gather ordinary matter. When galaxies eventually emerged, they were expected to be modest and faint, fragile assemblies that would require hundreds of millions of years to evolve into anything impressive. The universe, according to this idea, learned how to stand before it ever learned how to sprint. That assumption guided theoretical work for decades. So when the James Webb Space Telescope started to explore the universe's earliest epochs, astronomers were prepared to see very little. They expected rarity, a handful of primitive galaxies scattered across space, dim shapes barely holding themselves together in a cosmos still in its infancy. What Webb revealed instead was abundance. Again and again, bright galaxies showed up in periods that should have been almost empty. These were not weak glimmers on the verge of collapse. They were already active, complex systems forming stars at rates comparable to, and sometimes greater than, galaxies seen much later in cosmic history. The shock did not come from finding a single odd object. It came from the consistency of the results. Within the universe's first 500 million years, Webb detected galaxies pouring out extraordinary amounts of light. Some of them contained hundreds of millions, and in some cases even billions, of stellar masses worth of material. According to existing models, assembling that much mass should have taken far longer than the universe had been alive. Gravity is strong, but it works methodically. Gas has to shed energy before it can collapse. Dark matter halos must grow large enough to hold onto normal matter. Stars require millions of years to form, and those stars must live and die to enrich their environments with heavier elements. Each step sets a minimum timescale. Compress that sequence too tightly, and the physics no longer holds together. And yet, those galaxies were already present. One of the most unsettling parts of these discoveries was not only how large or how bright the early galaxies appeared, but how chemically evolved they were. Webb spectroscopic data showed clear signatures of carbon, oxygen, and nitrogen, elements that simply are not present in significant amounts immediately after the Big Bang. These elements are made inside stars. Finding them in such young galaxies points to an unavoidable conclusion. At least one earlier generation of stars must have already formed, burned through its fuel, and ended its life cycles, spreading heavy elements into space, all within the universe's first few 100 million years. The cosmic timeline was being pushed uncomfortably far backward. To understand why this was so troubling, it helps to picture galaxy formation as something like building a city. You cannot raise skyscrapers before you lay roads. You cannot pour concrete before steel exists. Every stage relies on what came before. The early universe was supposed to be setting foundations. Webb was revealing structures that looked finished. This growing gap between expectation and observation became known as the too much light, too early problem. When astronomers estimated how much total light galaxies should produce during the universe's first billion years, the numbers came out far lower than what Webb was seeing. The observations exceeded predictions by factors of 2, 5, and sometimes even 10. That is not a small mismatch. It is a clear signal that something is off. As they always do, scientists responded by questioning everything. They scrutinized the measurements. They checked the instruments. They went back through the data again and again. They asked whether dust, gravitational lensing, or observational bias might be making galaxies seem brighter or more massive than they truly were. Each time, the conclusion remained the same. The early universe was not faint. It was glowing. Some of these galaxies were so unexpectedly massive that researchers briefly labeled them universe breakers, objects whose very existence seemed to clash with the limits set by cosmology. According to standard models, galaxies that large should not exist at such early times, unless something fundamental about the universe's early development had been misunderstood. At first, there was hope that the masses had been overestimated. Perhaps the light was not coming only from stars. Perhaps supermassive black holes at galactic centers were adding extra brightness, making galaxies appear larger than they really were. Further analysis showed that this explanation helped, but only to a degree. Yes, some early galaxies do host intensely active black holes whose energy boosts their apparent luminosity. Accounting for that reduced the most extreme cases. But even after making those adjustments, the early universe still contained roughly twice as many massive galaxies as theory predicted. The tension softened, but it did not vanish. This pattern showed up repeatedly. Webb examined different patches of sky in different directions using different instruments and wavelengths. Each time, the message was the same. The early universe was crowded. Galaxies assembled rapidly. Star formation proceeded with remarkable efficiency. This forced astronomers to rethink a basic assumption: how effectively the universe could convert gas into stars. In the present-day universe, star formation is surprisingly inefficient. Most of the gas inside galaxies never turns into stars. It gets heated, stirred by turbulence, blown outward by stellar winds, or disrupted by radiation. A gigantic molecular cloud can drift through space for millions of years and still manage to produce only a relatively small number of stars before it finally breaks apart and fades away. The earliest galaxies, however, seem to have followed a very different set of rules. One explanation is that the young universe itself was far denser than it is today, with matter squeezed into tighter regions, causing gas clouds to collide much more often and collapse far more quickly. Another possibility is that the very first stars were born from almost pure hydrogen and helium, without heavier elements getting in the way of how the gas cooled and behaved. In those conditions, this simpler material may have collapsed more easily and more directly than the metal-rich gas we see forming stars now. Galactic mergers almost certainly mattered too. In the early universe, galaxies sat much closer together than they do today. Collisions were not rare events, they were common. When galaxies smash into one another, enormous amounts of gas are funneled toward their centers, squeezed to extreme densities, and that compression triggers intense waves of star formation. Instead of growing slowly over long periods, a galaxy could gain much of its mass in short, chaotic, and violent bursts. Each of these ideas helps explain part of what we observe, but none of them on their own fully solves the puzzle. At the hearts of many of these early galaxies sits another mystery altogether. Webb has revealed supermassive black holes already in place when the universe was less than 500 million years old. Some of these objects are millions, even billions, of times more massive than our Sun. By the standard rules of physics, this should not be possible. Black holes are thought to form when very massive stars collapse at the end of their lives, producing remnants that weigh perhaps a few tens of solar masses. From that point, a black hole can grow by pulling in surrounding material, but that growth faces limits. As matter falls inward, it heats up and releases energy, and that radiation pushes back, slowing further infall. Even in the most favorable conditions, building a black hole with a mass of 1 billion suns should take far longer than the early universe seems to allow. And yet, Webb continues to find them. This has pushed astronomers to seriously consider ideas that once sounded almost too extreme. It may be that some black holes formed through the direct collapse of enormous gas clouds, bypassing the normal star phase altogether. It could be that the first generation of stars grew thousands of times more massive than stars today, collapsing straight into large black holes. It may also be that black hole mergers were far more common in the dense, crowded early universe than we previously believed. None of these possibilities has been proven. None of them can be confidently dismissed. What makes this era so crucial is that these early galaxies and black holes shaped everything that came after them. Their intense radiation transformed the universe, tearing electrons away from hydrogen atoms during a period known as reionization. Their supernova explosions filled space with heavier elements. Their gravity gathered matter into the first large-scale cosmic structures. If they formed earlier and more efficiently than expected, then our entire timeline of cosmic history needs to be adjusted. And as Webb peers even deeper into space, a pattern begins to stand out. The universe did not take its time becoming complex. It moved fast. It assembled stars, galaxies, and black holes at a speed that strains our best equations, leading to a realization that is hard to avoid. If the universe could build so much structure so quickly, then what exists today, after billions more years of evolution, may be far larger than we ever imagined. That realization becomes even harder to ignore when Webb turns to something even more unsettling. It begins to count how many galaxies actually exist. For most of the 20th century, astronomers believed they had arrived at a reasonable answer to one of the biggest questions of all. How many galaxies are there in the universe? The basic idea was straightforward, even if the execution was difficult. Aim a powerful telescope at a tiny patch of sky that appears empty, count every galaxy you can see, and then scale that number up to represent the entire observable universe. When the Hubble Space Telescope carried out its deepest observations, it revealed nearly 10,000 galaxies packed into a region of sky no bigger than a grain of sand held at arm's length. At the time, that image was astonishing. From it, astronomers concluded that the universe likely contained a few 100 billion galaxies. The figure was almost impossible to truly grasp, and for many years it remained the accepted answer. Then the James Webb Space Telescope looked into that same darkness. Where Hubble saw black gaps between galaxies, Webb detected faint glows in infrared light. Where Hubble recorded barely visible smudges just above the noise, Webb uncovered structure. Areas that once seemed empty suddenly appeared crowded, layered, and full of distant systems that had gone unseen before. This wasn't a failure of Hubble. It was a matter of wavelength. As the universe expands, the light from its most distant galaxies is stretched, shifting into the infrared, exactly where Webb was designed to see. By the time that ancient light finally arrives here, it is no longer visible to human eyes in the way the Hubble telescope was built to observe. The galaxies themselves were never missing. Their light was always traveling through space, but it had shifted beyond what Hubble could detect. Webb was designed precisely to intercept that escaped light. In one of its most ambitious observing campaigns, Webb focused on a portion of the sky only a little larger than 3 full moons set side by side. For hundreds of hours, it stared without interruption, gathering more than 1,000,000 separate exposures, each one recording extremely faint infrared signals that had crossed the universe over immense spans of time. When all of those exposures were combined into a single image, the outcome was astonishing. Almost 800,000 individual galaxies appeared within that tiny slice of sky. That is 800,000 galaxies in a region most people would casually glance over and assume was empty. To appreciate what that really means, imagine taking the famous Hubble ultra-deep field and printing it on an ordinary sheet of paper. To reproduce the Webb image with the same level of detail, the print would have to be more than 13 feet tall and 13 feet wide, essentially a wall-sized tapestry of cosmic history. And every tiny point of light in that enormous mural is not a single star. Each one is a galaxy. Inside each galaxy are millions, billions, and in some cases even trillions of stars. Many of those stars are surrounded by planetary systems. Many of those galaxies contain complex chemistry, clouds of dust, and heavy elements created by generations of stellar birth and death. The universe, as it turns out, is not a thin scattering of lonely islands floating in darkness. It is crowded, layered, and richly structured on every scale we can observe. What makes this discovery even more remarkable is that Webb did far more than simply count how many galaxies are there. It measured them. For each galaxy, astronomers can estimate how far away it is, how massive it is, how quickly it is forming new stars, and roughly how old it is. With that information, scientists can reconstruct how galaxies evolved across nearly the entire lifetime of the universe, following their growth from the earliest cosmic dawn right up to the present era. When they began to do this, an even deeper pattern revealed itself. Galaxies are not sprinkled randomly through space. They gather together, they line up, they trace paths that are otherwise invisible. On the largest scales, the universe looks like a gigantic cosmic web made of long filaments of matter stretching tens and hundreds of millions of light years. These filaments intersect at dense hubs where clusters of galaxies form, and between them lie enormous voids where almost nothing exists. This overall structure had been predicted by theory for decades, but Webb revealed it with a level of clarity never achieved before. Many of the galaxies Webb detected were hidden behind thick veils of dust that block visible light, but allow infrared wavelengths to pass straight through. Entire populations of dusty, star-forming galaxies suddenly came into view, filling regions where previous surveys had seen little or nothing. The cosmic web did not simply sharpen into focus, it became far more crowded. This matters because the arrangement of galaxies is not decorative or accidental. It preserves a record of how the universe grew. Shortly after the Big Bang, matter was distributed almost evenly across space, with only tiny variations in density left behind from the universe's earliest moments. Regions that were just slightly denser than average exerted slightly stronger gravitational pull. Over time, matter flowed toward those regions, increasing the contrast. Gravity gradually sculpted space into filaments and nodes, drawing material out of surrounding areas and leaving behind vast, empty voids. A helpful way to picture this is rainfall over uneven land. Water flows into valleys, carving rivers and channels, while higher ground is slowly left dry. Over time, a structured landscape emerges. The universe evolved in much the same way, except that the flowing substance was matter itself. Webb's observations show that this process was already well advanced, surprisingly early in cosmic history. Filaments, tens of millions of light years long, were already in place when the universe was only a few billion years old. Some of these structures were so large and so orderly that they challenge our expectations about how quickly matter should be able to organize itself. One striking example is a structure astronomers call the cosmic vine. It is a chain of at least 20 tightly grouped galaxies, stretching more than 13 million light-years across. These galaxies existed when the universe was still young. Yet, the structure rivals much older formations in sheer size. What makes the cosmic vine particularly intriguing is not only how large it is, but what state it is in. Several of its biggest galaxies have already stopped forming stars. They are quiescent, meaning they have used up or lost the gas needed to create new stars. That is unexpected at such an early time in cosmic history, when most galaxies are still actively forming stars. What this tells us is that surroundings play a crucial role. Galaxies, growing up in crowded neighborhoods, follow a very different path from those left alone in quieter regions. Close encounters, repeated interactions, and mergers, combined with the intense conditions of packed cosmic environments, can push a galaxy to evolve faster, forcing it to grow quickly and exhaust its fuel early. This pattern isn't a one-off discovery. By using data from Webb, astronomers put together the deepest and most detailed catalogue of galaxy groups ever created. In total, they identified more than 1,600 galaxy groups and protoclusters, stretching across time from roughly 12 billion years ago to just a few billion years ago. These collections are the ancestors of the massive galaxy clusters we see today. By comparing groups at different distances, researchers are essentially watching cosmic architecture assemble itself over time. The earliest groups look messy and unsettled, filled with irregular galaxies forming stars at frantic rates. As time goes on, later groups appear calmer and more organized. Galaxies become smoother in shape, star formation begins to slow, and gravity gradually takes control over chaotic motion and incoming gas. This unbroken view across billions of years simply wasn't available before Webb. And yet, despite all this density and structure, the universe is equally defined by what isn't there. Between the glowing filaments of the cosmic web lie enormous voids, regions stretching tens to hundreds of millions of light-years that contain very few galaxies at all. These voids are not tiny gaps. By volume, they are the largest continuous structures in the universe. If you could somehow place yourself at the center of one of these voids and look in any direction, you would stare into darkness for tens of millions of light-years before seeing the nearest galaxy. Vast regions of space never gathered much matter, simply because gravity drew that material elsewhere. Webb's deep field images show this contrast with striking clarity. Within a single image, tightly packed clusters of galaxies sit right next to vast black areas that hold almost nothing. The universe is, at the same time, crowded and empty, abundant and sparse, carefully structured and deeply desolate, all depending on where you happen to look. This brings the discussion back to the numbers. If Webb's deep fields truly represent the universe as a whole, and multiple observations in many directions suggest that they do, then the total count of galaxies in the observable universe may not be in the hundreds of billions, but in the trillions. For every galaxy we once believed existed, there could be 10 more hidden beyond the reach of earlier telescopes. That shift in perspective changes everything. More galaxies imply more stars. More stars imply more planets. More planets imply more chances for complexity to emerge. The universe becomes not only larger, but far richer in what it can produce. And still, even this overwhelming abundance exists only within the observable universe. Beyond that limit, space continues, galaxies continue, structure continues, James Webb has revealed that even the portion of the universe we can see is far bigger and more densely populated than we once imagined. And that realization pushes us toward a deeper question. If reality is already this full within our visible horizon, what does that suggest about the scale of everything that lies forever beyond our reach? At first, the universe seems straightforward to measure. The Big Bang occurred about 13.8 billion years ago. Light moves at a constant speed, so it feels reasonable to think that the most distant objects we can observe should be about 13.8 billion light-years away. For a long time, even scientists spoke as though that picture were correct, but that simple intuition quietly fails the moment we take cosmic expansion seriously. The observable universe does not have a radius of 13.8 billion light-years. Its radius is about 46.5 billion light-years, giving it a total diameter of roughly 93 billion light-years. This isn't guesswork or imagination. It's a measured result, supported by observations of expansion and the behavior of ancient light reaching us from the early universe. The reason this number feels so strange is that it clashes with how we naturally think about motion. Nothing moves faster than light through space, and that rule still applies. No galaxy is tearing through space at impossible speeds. No signal is breaking any cosmic limit. Instead, the universe grows larger in a far subtler way. It does so by stretching space itself. When we say distant galaxies are moving away from us, it's tempting to imagine them flying outward like debris from an explosion. That image is deeply misleading. On the largest scales, galaxies are not really moving through space. They are being carried apart as the space between them expands. A simple analogy helps make this clear. Picture dots drawn on the surface of a balloon. As the balloon inflates, every dot moves farther away from every other dot. None of the dots sits at the center, and none of them is moving across the surface on its own. The surface itself is stretching, and the dots are simply along for the ride. The universe behaves in much the same way. When a distant galaxy released the light we observe today, it was much closer to us than it is now. Over billions of years, while that light was traveling toward Earth, the gap between us and distant galaxies has been stretching the entire time their light has been on its way. By the moment that light finally reaches Earth, the galaxy that sent it is no longer where it was when the light began its journey. It has been carried tens of billions of light-years farther away by the expansion of space itself. That is why we are able to see galaxies whose light has been traveling for 13.5 billion years, even though their present-day distance is more than 46 billion light-years. Light is not moving across a static backdrop. It is traveling through space, while that space is continuously growing. In a very real sense, light has been running on a cosmic treadmill. Early in the universe's history, expansion was gentler. Light made reliable progress, steadily closing the distance as time passed. Later, expansion began to speed up, stretching space more rapidly, pulling galaxies apart faster and faster. Some photons still managed to reach us because they set off early, before the expansion became dominant. Others never will. From this behavior emerges a boundary called the cosmic horizon. The cosmic horizon is not a physical barrier, not a wall or an edge you could point to in space. There is no location where the universe suddenly ends. Instead, it marks the maximum limit of what can ever be observed from our position, given the universe's finite age and the way space expands. Beyond that limit, light cannot arrive. not because it has not had enough time, but because the space it must cross expands faster than light can move through it. And this is where the universe starts to feel genuinely unsettling. Space does not stop at the cosmic horizon. We know this because the universe appears essentially the same in every direction we look. The number of galaxies does not fade toward an edge. The cosmic microwave background, the faint afterglow left behind by the Big Bang, looks remarkably uniform across the entire sky. That smoothness would be impossible if space simply ended just beyond what we can observe. So the universe continues beyond our view, but in a way that permanently conceals much of itself. Beyond 46.5 billion light-years, galaxies still exist. Stars continue to form and burn out. Black holes still collide and merge. Entire cosmic histories play out in regions that will never affect us, and that we can never affect in return. No signal from those places will ever reach Earth, not because our instruments are too limited, but because the structure of space-time itself forbids it. Even more unsettling is the fact that this boundary does not stay fixed. As time goes on, the observable universe grows because light from increasingly distant regions has had more time to arrive. The horizon slowly moves outward. At the same time, cosmic expansion is accelerating, driven by dark energy. Space today is stretching faster than it did in the past. These two effects work against each other. The result is a universe in which some objects become visible for a time, only to later slip permanently beyond reach. Galaxies we can observe now are not guaranteed to remain observable forever. Their light keeps stretching, shifting toward longer and longer wavelengths. Eventually, it becomes so faint and so redshifted that no telescope, no matter how powerful, could ever detect it. From our point of view, those galaxies will seem frozen at a specific moment in their history, gradually dimming until they disappear entirely. This is not a speculative idea. It follows directly from measurements of how fast the universe is expanding. If the universe continues to behave as it does today, then in about 100 to 150 billion years, every galaxy outside our local, gravitationally bound group will cross the cosmic horizon. Observers in that distant future would see a universe made up of only a small cluster of nearby galaxies, surrounded by darkness. The signs of cosmic expansion, the cosmic microwave background, and the vast network of distant galaxies would be gone. They might never realize that anything else ever existed. This forces a deep shift in how we think about reality. The observable universe is not the universe itself. It is simply the portion that happens to be visible from where we are at this particular moment in cosmic time. Move to another galaxy, and the observable universe changes. Some galaxies come into view, others vanish beyond the horizon. Every location in space has its own observable universe. This leads to situations that feel strange and counterintuitive. Two galaxies can both be visible from Earth, yet unable to see one another. They may sit on opposite sides of our horizon. Light from both reaches us, but light from one cannot reach the other. From their perspective, Earth itself may lie beyond their cosmic horizon. There is no special viewpoint, no central location, no place from which the entire universe can be seen. Every observer, wherever they are, occupies the center of their own observable bubble. This is why the James Webb Space Telescope is so transformative. By extending our view closer to the cosmic horizon than any instrument before it, Webb compels us to face the ultimate limits of observation itself. When it picks up galaxies at extreme redshifts, it isn't simply revealing very old objects. It is showing us the boundary of cause and effect. The light from those galaxies began its journey when the universe was young. But those galaxies are no longer where that light originated. Their present condition, their later collisions, reshaping, or even their destruction is information we can never access. That knowledge is still on its way, carried by light that is being stretched thinner and thinner as space expands, and in many cases it will never reach us at all. What we observe is not reality as it is now, but reality as it once was, and even that picture is incomplete. Beyond the observable horizon lies the unobservable universe, regions forever hidden from us, which may contain galaxies, clusters, and structures every bit as intricate as the ones we can see. Some theories suggest the universe could be infinite, while others argue it is finite yet unimaginably vast. Whichever is true, the part we can observe is almost certainly only a tiny portion of the whole. James Webb has not uncovered the edge of the universe. It has shown us that there is no edge we can ever reach. As that realization settles, another question becomes impossible to ignore. If expansion hides most of the universe from us, if enormous parts of reality are permanently inaccessible, then something must be causing that expansion to speed up. To understand that influence, we have to confront the most powerful and most mysterious component of the cosmos itself. For much of the 20th century, the narrative of cosmic expansion seemed clear and reassuringly simple. The universe began with the Big Bang. Everything moved outward, and gravity slowly worked to slow that motion down. Scientists debated the ending, whether expansion would continue forever or reverse into a collapse. But the basic assumption remained unchanged. Gravity ruled the universe. That assumption did not survive confrontation with precise observation. In the late 1990s, astronomers examining distant stellar explosions encountered a deeply troubling result. These explosions, called Type E supernovae, shine with an almost uniform brightness. Because of that consistency, they serve as reliable cosmic distance markers. By comparing how bright a supernova appears to how bright it should be, researchers can determine how far away it is. Combine that distance with how fast its host galaxy is moving away, and reconstruct the expansion history of the universe. What emerged from those measurements was the opposite of what theory predicted. Expansion was not slowing. It was accelerating. Distant galaxies were farther away than they should have been if gravity were gradually easing the expansion. Something was actively pushing space apart, not merely allowing expansion to continue, but making it speed up. The deeper astronomers looked into the past, the clearer this pattern became. For billions of years, expansion had been accelerating. To explain this behavior, cosmology had to introduce a new ingredient: dark energy. Dark energy is not something we can see, touch, or measure directly. It emits no light, absorbs no radiation, and does not gather into stars, galaxies, or clouds. Its presence is known only through its effect on the expansion of the universe, and that effect dominates everything. Current measurements show that dark energy accounts for roughly 68% of all that exists. Ordinary matter, everything from galaxies and stars to planets and people, makes up less than 5%. Dark matter constitutes most of what remains. The universe that feels tangible and familiar to us is a small minority of reality. What makes dark energy especially disturbing is how it behaves as the universe grows. Normal matter becomes more spread out as space expands. Double the volume of space and the density of matter is cut in half. Radiation thins out even faster. Dark energy does not behave this way. Its density stays constant even as space expands. As the universe grows larger, the total amount of dark energy increases. This creates a self-reinforcing cycle. More space produces more dark energy. More dark energy drives faster expansion. Faster expansion creates even more space. Over immense spans of time, this feedback loop has completely reshaped the universe. In its early history, matter dominated, and gravity carved galaxies, stars, and the vast cosmic web. But as expansion continued and matter grew more diffuse, dark energy gradually took control. Around 5 billion years ago, it became the dominant influence on cosmic expansion. The James Webb Space Telescope does not observe dark energy directly, but its effects are written across everything Webb sees. The extreme stretching of ancient light, the enormous scale of the observable universe, and the way distant galaxies race away from us all carry the signature of this unseen force. Without dark energy, the universe would be far smaller. The cosmic horizon would be much closer, and many of the distant regions we can observe today would never have come into view at all. Dark energy does not only influence what the universe looks like right now, it plays a decisive role in shaping what the universe will become. If dark energy truly stays constant, as observations currently indicate, then cosmic expansion will never slow down. Instead, it will keep accelerating as time goes on. Groups of galaxies held together by gravity will remain intact, but anything beyond those regions will slowly drift away, slipping past the cosmic horizon, far into the future. Trillions of years from now, observers living inside a galaxy similar to the Milky Way would experience an increasingly isolated universe. Nearby stars would still fill the sky, but beyond that, space would appear almost empty. The universe would still be there, vast and real. Yet, from that perspective, it would seem nearly vacant. This apparently simple picture becomes far more complicated because of one of the most serious, unresolved questions in modern cosmology, a problem that the James Webb Space Telescope has not resolved but has instead made impossible to ignore. When scientists try to measure how fast the universe is expanding today, they do not arrive at a single value. They consistently find two different answers. One approach looks deep into cosmic history by examining the cosmic microwave background, the faint relic radiation released when the universe was only about 380,000 years old. From tiny variations in that ancient light, researchers infer an expansion rate of roughly 67 kilometers per second per megaparsec. The second approach focuses on the nearby universe. Astronomers measure distances to galaxies using Cepheid variable stars and type Ia supernovae, then compare those distances with how quickly the galaxies are moving away from us. This method repeatedly produces a higher expansion rate, close to 73 kilometers per second per megaparsec. Both techniques are highly precise. Both have been tested again and again. Both have been examined carefully for hidden errors. Yet they disagree. This conflict is known as the Hubble tension, and it represents one of the most serious fractures in our current understanding of the universe. James Webb was expected to help resolve this disagreement by offering sharper and more reliable distance measurements. Instead, Webb reinforced the higher expansion rate seen in the nearby universe. The disagreement did not fade. It became more pronounced. As a result, cosmology now sits in an uncomfortable position. Either there is a flaw in our measurements, or there is a flaw in our assumptions, or there is something fundamentally missing from the models we use to describe reality. One possible explanation is that dark energy is not truly constant. Its influence may have changed over cosmic history, subtly altering the expansion rate in ways our current theories do not fully describe. Another possibility is that unknown physics affects how light travels across enormous distances, gently skewing our measurements without us realizing it. Or it could be that the early universe behaved differently than we assume, leaving behind an expansion pattern that evolves in unexpected ways over time. Each of these possibilities carries enormous implications. The expansion rate sets the universe's age, its overall scale, and its long-term destiny. If we have misunderstood it, then many conclusions built over decades of cosmological research may need to be reconsidered. This is not a minor technical issue. It strikes at the core of how we describe the universe itself. There is also a more extreme scenario that cannot yet be completely dismissed. If dark energy grows stronger with time instead of remaining constant, expansion could eventually overpower gravity even on relatively small scales. Galaxy clusters could be torn apart. Individual galaxies might lose their structure. Star systems, planets, molecules, and eventually even atoms could be pulled apart in a speculative future known as the Big Rip. Current observations do not favor this outcome, but uncertainties remain. Measuring dark energy with precision is extraordinarily challenging, and even slight changes in its behavior could have dramatic consequences over vast timescales. What is already beyond doubt is that dark energy dominates the universe. It stretches space itself. It hides enormous regions of reality beyond our observational reach. It determines what future observers will be able to see. It is the reason the observable universe spans 93 billion light years, and it is the reason most of existence will remain forever invisible to us. And yet dark energy alone cannot explain the universe we observe. While it pulls space apart on the largest scales, something else must pull matter together on smaller ones. Something must counter expansion locally, allowing galaxies to form, clusters to grow, and structure to emerge instead of dissolving into a smooth, featureless fog. That influence is just as invisible, just as mysterious, and just as essential. To understand how the universe maintains structure while it expands, we must look to the unseen framework that shapes every galaxy, every cluster, and every filament of the cosmic web. If dark energy governs how the universe expands, then dark matter governs how it holds itself together. Without it, the universe revealed by the James Webb Space Telescope would not exist in any recognizable way. Galaxies would never have formed, clusters would have drifted apart, and the vast network of filaments spanning the cosmos would have remained an almost uniform haze of matter. Dark matter does not glow, it does not block light. It does not emit radiation of any kind that we can directly observe. And still, it outweighs everything we can directly observe by more than 5 to 1. Around 85% of all matter in the universe is dark matter, something we cannot see at all, known only because of the gravitational pull it exerts. Every star, every planet, every cloud of gas, and every galaxy exists inside a structure dominated by something fundamentally invisible. The earliest hints that this hidden component existed appeared almost a century ago, when astronomers realized that galaxies were behaving in ways that simply didn't add up. In spiral galaxies, stars far from the center were moving far too quickly. Based on the gravity produced by visible matter alone, those stars should have escaped into intergalactic space. Instead, they stayed bound, orbiting as if each galaxy was surrounded by a vast, unseen halo. That unseen mass was dark matter. As observations improved, the evidence became impossible to dismiss. Entire clusters of galaxies showed the same issue on much larger scales. Individual galaxies within clusters were moving too fast to be held together by stars and gas alone. Gravitational lensing revealed bending and stretching of background galaxies far stronger than visible matter could explain. Over and over again, the message was the same. Most of the matter in the universe cannot be seen. What makes dark matter so crucial is not only how much of it there is, but how it behaves. Unlike ordinary matter, dark matter does not collide with itself, and it does not lose energy by emitting light or any other radiation. It moves through space almost without resistance. Because of this, it was able to start clumping together extremely early in cosmic history. Shortly after the Big Bang, the universe was nearly smooth, with only tiny variations in density left over from its earliest moments. Dark matter responded to those variations first. While normal matter remained hot and resisted collapse, dark matter quietly gathered into ever-growing concentrations, forming enormous invisible halos long before the first stars ever switched on. These halos became the underlying framework of everything that followed. As the universe cooled, ordinary matter began to fall into these dark matter wells. Gas accumulated, became denser, and eventually ignited nuclear fusion. Stars were born. Galaxies took shape, not by chance, but precisely in the places where dark matter had already assembled. What we see today is a visible universe that traces an invisible plan laid down billions of years earlier. This process created one of the most remarkable features of reality, the cosmic web. On the largest scales, matter is arranged in immense filaments stretching tens to hundreds of millions of light-years across. Where these filaments cross, dense knots form, giving rise to galaxy clusters. Between them lie vast voids, regions so empty they contain almost no galaxies at all. This structure is not a coincidence or an artistic pattern. It is the natural result of gravity acting on dark matter over immense spans of time. Observations from James Webb have brought this structure into clearer focus than ever before. By identifying hundreds of thousands of galaxies and measuring how far away they are, astronomers can now map the three-dimensional distribution of matter across the cosmos. The pattern is unmistakable. Galaxies line up along filaments, gather at intersections, and avoid enormous empty regions. The visible universe follows an unseen skeleton. What makes Webb especially powerful is its ability to peer through dust and detect faint, distant galaxies that earlier surveys simply could not see. This fills in missing pieces of the cosmic web and reveals how early these structures formed. Webb has shown that filaments were already well developed when the universe was only a few billion years old, and that matter was flowing along them into growing clusters. This flow is not just a figure of speech. Both simulations and observations show that gas streams along dark matter filaments, like traffic, moving along vast cosmic highways. Galaxies grow not only by forming stars within themselves, but by continuously pulling in fresh material delivered along these invisible routes. Our own galaxy is part of this story. The Milky Way sits on a filament that connects to larger structures, drifting through space along paths defined by dark matter. On these enormous scales, motion is guided, not random. For many years, the idea that dark matter shapes the cosmic web rested mainly on simulations and indirect clues. Recently, though, astronomers managed something extraordinary. They detected dark matter directly along the filaments themselves. By using gravitational lensing, Scientists measured the tiny distortions in light from distant background galaxies as that light passed through regions where filaments were expected to be. The effect was extremely subtle and difficult to measure, but it was there. Those distortions revealed mass in places where visible matter could not possibly explain it. Dark matter was never confined only to dense clusters. It was drawn out across enormous distances, stretched through space, weaving everything together. This changed the cosmic web from a clever idea on paper into something we could actually observe. The universe is not a random scatter of galaxies slowly drifting away from one another. It is a connected system, a vast network whose shape and stability are controlled by matter we cannot see. The densest points in this network are galaxy clusters, the largest gravitationally bound structures that exist. One cluster alone can hold hundreds or even thousands of galaxies, along with immense stores of superheated gas and staggering amounts of dark matter. These clusters act like deep wells, pulling matter along long filaments toward their centers. When galaxies are drawn into a cluster, they do not remain unchanged. The crowded environment tears away their gas, shuts down the birth of new stars, and reshapes their structure. James Webb has observed these moments in remarkable detail, catching galaxies in the middle of transformation as their surroundings actively alter them. This tells us something crucial. The cosmic web is not frozen in time. It is alive, dynamic, and constantly rearranging the universe. And yet, despite its profound influence, dark matter itself remains one of the deepest puzzles in physics. We still do not know what it is. It could be made of particles that lie beyond the standard model, or it could point toward entirely new physical laws we have yet to uncover. After decades of searching, dark matter has never been detected directly in a laboratory, but its existence is impossible to deny. The rotation of galaxies, the bending of light through gravitational lensing, and the patterns seen in large-scale surveys all lead to the same result. Take dark matter out of our equations, and the universe we see simply would not hold together. James Webb does not reveal the true nature of dark matter, but it reinforces how essential it is. By showing how rapidly structure appeared in the early universe, Webb makes it clear that ordinary matter alone could not have formed galaxies so quickly. Dark matter supplied the early gravitational framework, giving galaxies a head start just a few 100 million years after the Big Bang. It also explains the universe we see today. Vast empty voids, densely packed clusters, and the long filamentary bridges linking them all arise naturally when dark matter dominates gravity. But this invisible scaffolding exists within a universe being pulled apart by another unseen force. Dark matter builds structure while dark energy stretches space itself. The universe lives in a balance between the two. On smaller scales, gravity wins and galaxies form, clusters grow, and the cosmic web thickens. On the largest scales, dark energy takes over, driving galaxies apart and pushing regions of space beyond our cosmic horizon. James Webb has shown us that the universe is not just bigger than we once thought. It is more structured, more interconnected, and more dependent on invisible forces than we ever imagined. Everything we see, stars, galaxies, and glowing nebulae, is only the visible surface of a much deeper framework, an unseen architecture holding reality together. And when we step back far enough to consider that structure as a whole, one truth becomes impossible to ignore. Even this immense, connected universe is only the part we can observe from where and when we exist. Beyond that boundary, the universe continues, shaped by the same hidden forces, unfolding far beyond any horizon we will ever cross.